Log on, tune in, find out. Another good idea from Cambridge.
Move back to computability theory. Our next speaker is George Barmpalias, who got his degree in 2004 from the University of Leeds. Actually, he's one of Barry's PhD students. And had postdoc positions in Leeds, Wellington, New Zealand, Amsterdam, and at the Chinese Academy of Sciences since then. I heard that he is going to give the definition of the Turing degrees that was missing in our first talk today. So those of you who complained that they didn't know what the Turing degrees are, this is the talk to listen to. George.
Thank you. So I'm going to be talking about reducibilities in the theory of computation in general, and more particularly in computability theory and some recent developments, new reducibilities in algorithmic randomness and the part of computability which is close to that area. So reducibilities are basically, it's a general talk. They're tools in order to classify complexity of problems. There are tools, mathematical tools, we can use to compare the complexity between two problems. So we can say one problem is more complex than another in some sense. Well, first of all, let's clarify how we talk about problems, what we mean about problem. When we say problems, we mean tasks of the type given some input value x, usually discrete, to determine a yes or no answer, whether it belongs to a set or not, it has a property or not, or to compute a value, determine a value y. So these kind of problems, most of these problems can be coded into binary sequences. So when the input value is ranges over an infinite domain, you get infinite binary sequences, right? So we may identify a problem of this type with infinite binary sequence, or if we see infinite binary sequences as characteristic sequences of sets of positive integers, then we can also talk about a problem being a set of natural numbers. So I'm going to switch back and forth between the two. It's the same thing. Generally, I'm going to say that these sequences are reals, and the whole space, sometimes we call it the Cantor space. Some examples of problems from mathematics and computer science are, for example, come from presentations of groups. Given a presentation of a group to determine, with some equations, words, to determine whether it's the identity, given two presentations, determine if they represent the same or isomorphic groups, and so on. Given a Diophantine equation to determine whether it has a zero or not, or given a propositional formula whether it has a satisfying assignment. Of course, there are many more problems like optimization problems, verification of programs, and so on. But in order to have a general theory, we may just look at some infinite binary string, even if we don't have a problem in mind associated with that string. Okay, so the thing is that the problems we really care about, there are very few. The reals are too many. But I'm going to be focusing on the general theory of reducibilities on the reals. So reducibility is a pre-order. So it's a relation which is transitive and reflexive. And there is a reason for that. We want to use these things to model what I said at the beginning. So if a problem is at least as hard as itself, right, that's reflexivity. And also if a problem A is simpler than B, problem B, and problem B is simpler than problem C, then problem A should be simpler than problem C. So these are reasonable requirements. And when we, of course, a reducibility must have some intuition connected to measuring complexity. But what happens is that essentially we reorder the continuum, the real numbers, according to, in terms of complexity. So the real numbers are not linearly ordered anymore, but if a real is above another real, it means it's more complex. Okay. That's one of the main tools we have in the theory of computation for measuring complexity. In practice, reducibilities are used in order to prove intractability of problems. So if we know that the problem is intractable and we can reduce it to another problem, then the second problem must be intractable, right? But in general, it's a way for measuring complexity. The other main way we have, or tool to classify problems according to complexity, is hierarchies. So these are sequences of classes of reals, okay, of increasing complexity. For example, the arithmetical hierarchy, we look at sequences and how complex definitions they have in arithmetic, for example, count the quantifier alternations, and sequences with complicated definitions are more complex, which don't have simpler definitions, and so on. So we get a sequence of classes starting with the simple ones and moving to more complicated. And we have analogs in lower complexity classes, for example, the polynomial hierarchy. And a difference hierarchy has to do with the difficulty of enumerating, algorithmically enumerating a set of natural numbers. So I'm not going to define everything. The jump hierarchy has to do with the difficulty that a problem, the difficulty that a problem, how difficult your problem becomes if the real is used as a parameter. So if you take the real and as a parameter in a more complicated problem, whose definition involves some quantifiers over the parameter, then the more high the real is in the jump hierarchy, the more difficult the problem is to solve. Okay. So if a remark about the arithmetical hierarchy and the polynomial hierarchy is basically that they have very similar definitions. The polynomial hierarchy is a miniaturization of the arithmetical hierarchy, starting with the problems which are solvable in polynomial time and applying quantifiers in a bounded way. But whether the polynomial hierarchy collapses is an open problem, while the arithmetical hierarchy doesn't collapse, and that was known even from the 40s. So that's a point where the theory of feasible computation and the theory of incomputability took different ways of development, right? So a basic result in computability theory is the unsolvability of the halting problem, which says, given a machine, a program decide whether it halts or not. But this doesn't exist in complexity theory. It's basically the P equals NP problem, which is open. So most of the development of incomputability theory, and in particular the theory of Turing reducibility, which we're going to see soon, depends on this result, the unsolvability of the halting problem. But there is no such analog known in complexity theory. So naturally, people started doing different things. Of course, it is possible to do degree theory reducibilities in complexity theory, but usually you have to work with an assumption that P is not equal to NP. Okay, let's see. The general notion of complexity or computation is basically that a set of natural numbers is computable if you can write a program in some universal language, say C++, that solves the problem. So given any input, it replies any number, it replies whether the number is in the set or not. That's theoretically computable because we don't care about resources like time and memory that is needed in this computation. Okay, this is basically the Turing machine model. Another way is to say that it's computable if it's definable in some way in arithmetic. That's a much weaker notion of computation. And the two are related, of course. It's feasibly computable if it's computable in some realistic sense, for example, in polynomial time or in a suitably bounded space memory. But some problems are incomputable, like the halting problem. And another notion of complexity is randomness. So we don't only care about the information coded into the sequence, what problem it solves, but we care about how the answer to the problem is coded in the sequence. In other words, if a sequence, each of the initial segments of the sequence are very complex, then we say it's random. Well, I'm going to define this later on more precisely, but in computable, that doesn't have to, an incomputable sequence doesn't have to have very complicated segments necessarily. It could have trivial bits, like every second bit 0, but the odd bits, the even bits could be very complicated. So it's not random, but it may have very high information content. So these are some notions of complexity in general. And the fact is that you can, in these definitions in particular, you can very easily introduce a parameter and say that a real A is computable in another real B. You just have to let the machine have access into this external bit of information, the real B. So the program is an algorithm which can issue queries to B, which is called, by the way, an oracle. That term was introduced in Turing's 1939 paper. Okay. So you could say A is definable in B if B is involved in the definition, some arithmetical definition of A, or feasibly computable in B, or random in B. A is less random than B, and so on. We're going to see these in detail, but the fact is that for these kind of notions of complexity, the relativization is pretty straightforward, and it often gives rise to reducibility. Right. So let's see the main reducibility here is Turing reducibility. So A is Turing reducible to B if A is computable from B. So if there is a program which issues queries to B, and if it receives the right answers, then it outputs the answer about A. Okay. So we say that two sets have the same information, or they are Turing equivalent. That's an equivalence relation. If A is computable from B and B is computable from A. Okay, so in a way, so these equivalence classes are called Turing degrees, and they are supposed to be information content. So two reals in the same degree represent the same information, but coded in different ways, perhaps. Okay. The equivalence class, the Turing degrees, are ordered naturally by the reducibility. So we get a partially ordered set, which is a reordering of the continuum. Okay, all these countable classes are, all these equivalence classes are countable. So the reordering of the continuum according to Turing reducibility looks like that. There is a list element, which are the computable elements without any oracle, but by a Turing machine, a program without any queries to external sources. And there are certain significant elements, points, like 0 prime. 0 prime is the degree of the halting problem, and a lot of other problems in mathematics. And also, you can iterate this operation and get higher problems, higher degrees. So we have a natural way to, given a degree, to get a successor. Okay, that's a jump operation. It's a very complicated structure. There are minimal elements, non-zero minimal elements. There is a least upper bound for every pair of degrees. The structure of degrees below 0 prime is quite rich. That was known from the 1954 paper of Kleene and Post. And also the problems, the sets that can be enumerated by a machine, which are called the computably enumerable sets, are a proper subclass of this class. Is the inner part, and these form a very complicated set of degrees as well. There are many initial segments of the structure, some of them uncountable. Every degree has only countably many predecessors, but uncountably many successors. And there are a lot of minimal pairs. Almost all pairs are minimal pairs in this structure, and there are a lot of other things known about this structure. So this structure was defined in, was basically studied in 1954 in the paper of Kleene and Post, where they established the basic results. And before that, Post had already defined the reducibility, and he also introduced a number of easier, more tractable reducibilities, sometimes called strong reducibilities. For example, truth table, many one, and others. Well, this is not introduced by Post, but the idea is that the queries in these stronger reducibilities are issued in a more well-behaved manner. So many one indicates one positive query. Truth table indicates queries in the form of a truth table. So a conjunction or disjunction of positive or negative queries, and so on. So a lot of problems that are open for, occasionally open for Turing reducibility are sometimes looked, examined in the case of strong reducibilities. And this started already with Post, even before 1954. There are other reducibilities that correspond to different notions of complexity. For example, the difficulty to enumerate a set by a machine using some kind of information. So a set A is enumeration reducible to another set. If given an enumeration of the second set, you can produce an enumeration algorithmically using a machine of the first set. You can have more general notions of computations, like the definability I mentioned before, giving rise to arithmetical reducibility, and a lot of other reducibilities, hyperarithmetical and beyond. But in all of these reducibilities, there is a guiding principle, which is computability is some kind of definability, and vice versa. So if you can compute something, you basically have a definition of it in some language, and that language is very, very close to arithmetic. So, and vice versa, if you have an arithmetical definition, in some sense you can compute it using some oracle. Okay, so this link between computability and definability plays a role in, sometimes it's hidden, but plays a role in most proofs in classical recursion theory or computability theory. It's very important. And remember that, because in some new reducibilities, which I'm going to introduce now, this link will break. So a lot of arguments will break with that, and we'll see what the problems are. So this is some collection of people who developed degree theory, Turing degree theory, up to the 80s. I haven't put everyone here, but just a sample. So Turing didn't define Turing reducibility. Okay, Post defined Turing reducibility, but he did define oracle machines. Okay, he did define computation via Turing machine, and also using some oracle machines. And Post took that and he defined reducibility and the degrees, and in his paper with Clini, they proved the first results about this structure, mainly using bare category methods, essentially. And in the 60s and 70s, some major techniques were introduced, for example, by Gerald Sachs and Lachlan, which made the subject quite technical. And well, already by the 70s, he had developed in a quite technical, esoteric subject. And by the end of the 80s, I think it's fair to say that it's sort of not many logicians were very interested in the main results in recursion theory or computability theory. Now that has changed in the last 10 years. So people in computability theory are have paid a real effort to connect with other areas. For example, algorithmic mathematics, find algorithmic content in mathematics, ergodic theory, and so on. So the traditional themes in degree theories are the following: the algebraic study, the study of the structure as an upper semilattice. I said that there is a supremum always. The embeddings of lattices, for example, the study of ideals, automorphism, and the logical study look at decidability, in particular undecidability of decidability and decidability of theories and fragments of theories, and definability. A general theme that runs in this topic is global versus the local structure of the Turing degrees and the theory. Some local aspects involve the computably enumerable degrees, which I showed you in the picture before. It's a very complicated structure. So people study lattice, finite lattice embeddings, and so on. So a lot of these problems have remained open. The lattice embedding problem, for example. So globally, category and measure play a significant role. The first arguments in degree theory, the post-Clini arguments, were bare category arguments, initial segment constructions, where basically the idea about category and both category and measure is that, especially measure, is that instead of constructing a degree with specific properties, you just show that the class of degrees with that property is very big. In a bare category sense, is a comeager set, or some effectively comeager set. In measure theory, you show that it's measure 1. It can either have measure 0 or 1 if it's measurable, because of Kolmogorov's 0-1 law, because degrees are invariant under finite differences. If you change an infinite binary sequence at finitely many places, you get the same problem, essentially. Okay. So a lot of things can be proved by these methods, but these methods have other uses as well. For example, measure theoretic methods relate to randomness. So if you prove that the measure of the sequences, the reals which satisfy a property is 1, it means that a sufficiently random element will have this property. So in a way, you study the properties of typical degrees, typical sequences. And the same for category, only that the notion of typicalness is different. Right? So sufficiently generic reals have certain properties. By the way, it doesn't necessarily mean that if you look at, say, a definable property in the degrees, it doesn't mean that the set of reals that satisfy it is measurable. And it doesn't mean that it's meager or comeager. In fact, that depends on the axioms of set theory, even for definable properties in the degrees. But practically, in the properties we're looking at, usually we get measurable sets. So another notion of complexity, as I mentioned, is randomness. So a set may have a lot of information, but it may be coded in such a not in a very dense way. But if it's coded in a very dense way, so in n bits, basically every single bit carries important information. So if you omit some bits, you lose a lot of information. Then it's random. So for a mathematical definition of this notion, Kolmogorov came up with this, the idea of incompressibility. He said that a stream, an infinite binary sequence, is random if all of its initial segments are incompressible. What does this mean? Well, they're very hard to describe. So say that to describe the first 10 bits of a sequence, you more or less need at least 10 bits. Okay, that was the intuitive idea. Now, descriptions need to be defined mathematically, and for that he used Turing machines. So given a Turing machine M, you say that program sigma, that's a finite binary sequence, is a description of the sequence tau if it is the output. If the output of the machine under sigma is tau. It's a description relative to M. And he said that the complexity of a binary string is the length of its shortest description. So a complex string has relatively long descriptions, and simple strings, like a string of 100 zeros, can be described very easily by writing a very short program that prints 0 100 times. Okay. Yeah.
Ask a question to sort of focus my mind better. If you like, with this concept of complexity, there is a dependency upon the domain within which the string is initially chosen.
Sure.
If the domain has a unique element, then there's no problem.
Yeah, there is an obvious dependency on the machine, right?
And the
its
domain from which the element might be chosen.
Sure. I'm going to get rid of this dependency in the next slide.
Okay.
So this obviously depends on the machine. And well, one way to get rid of this dependency is, well, first of all, realize that any machine can have, any string can have a very short description if you choose the right machine, because you can hardwire the string into the machine, and then it trivially gives the shorter description it has to that string. So basically, but if you do that, you will increase the size. If the string you're trying to describe is really complex, you will increase the size of the machine, because you're hardwiring the sequence into the machine. So you have to take care of, you have to consider the size of the machine. Okay, so you can get rid of the dependency of the machine if you involve it in the definition. So the complexity of sigma is the least sum of the machine plus the complexity of the string under the machine, where M ranges over say, all Turing machines. Okay, that's one way to say it. So you get a notion of complexity in this way, which doesn't depend on the machine, but basically it's invariant, modular, and additive constant, because basically the complexity depends on the encoding of the machines that you have. Okay, of course, you have to choose a reasonable way to measure the size of the machine, but more or less, you just if you choose a different encoding, you get a different constant. So the theory is doesn't depend on the on constants, as you see later. So in this way, we may say that a string is C compressible for a constant C if it has a description that is shorter than its length by at least C bits. So if C bits are not really used, they don't really carry information. Now, there is a remark here that basically we want the complexity to represent exactly the number of bits which carry information. Now, if you describe a string tau with a string sigma, you can actually, using any Turing machine, you can actually use more than the bits of sigma to code information. You can use the length of sigma. So you can code information into the bits of sigma plus some information into the length of sigma. So given you feed sigma into the Turing machine reads the bits, but it can also read the length of the string. And the length is a number, which may code some additional information. So that's a drawback, but it was quickly fixed by Chaitin and Levin in the 70s by restricting the Turing machine, the class of Turing machines which decode programs. Okay, I don't think I need to get into the details of that, but these machines are called self-delimiting, which means they read the bits of the string and they stop when they've read all the bits without calculating the length. Well, what you get with this modification is what Kolmogorov originally wanted, which is this definition. A stream x is random if there is a constant c such that the complexity of the first n bits is at most n minus c, which is what I mentioned at the beginning. It's random if to describe the first n bits you need n bits, basically. So all the definitions will depend on a constant, because the definition itself is not invariant under constants. What's that? So this notion of randomness is very robust. It's not just a notion, it's a framework. It's a framework because you can relativize it to oracles, you can modify some technical properties of the complexity or the machines, and basically you get a whole range, a spectrum of randomness notions at various levels, and they're very robust. For example, this, which is sometimes called Martin-Löf randomness, coincides with other approaches based on measure theory or martingales betting strategies. The random reals form a set of measure 1 as expected. Most reals are typical. They meet various laws of large numbers, normality, and so on. And as I said, they are easily relativizable, so that we can say a real is random relative to another real. A very hot topic in algorithmic randomness at the moment, in the last 5 years at least, is lowness. It's the other end. Basically, infinite binary sequences which have very, very simple descriptions. And so what does it mean, simple? It means simple, it means as simple as a trivial sequence, the sequence of all zeros. That's a trivial complexity. So Kolmogorov complexity in this form is not a computable function, but this is pretty low. In particular, is bounded by 2 log n. Okay, so why is this area interesting? Well, for a start, there are non-computable streams with trivial initial segment complexity. So you may have an infinite binary sequence which cannot be computed, it means totally, by a Turing machine, every single bit, but it has very low complexity. So as far as the complexity of its initial segments is concerned, it's as simple as the sequence of zeros. Okay, so that's first proved by Solovey in the 70s, and it turned out that this class of sequences is very interesting, and a lot of the harder problems in the area are related to this class, which is called the K-trivial reals. K for the complexity, and trivial because it's a triviality notion. So now we want to, I said we can relativize this notion, but how do we get the notion of a sequence being more random than another? For Turing reducibility, it was quite easy because we just introduced an oracle. But here, it's not the same thing. But there is a very straightforward way to do that. We can say that y is at least as random as x if its initial segments have higher complexity than those, or at least as high as those of x, right? It's just an inequality. So if for some constant, constants are always involved, right? In fact, they give sigma 3 definitions of all these notions. The complexity, for each n, the complexity of the first n bits of y is higher than the complexity of the first n bits of x minus a constant. So the notation is this, and sometimes this is called the K-reducibility. So this reducibility was introduced in the last 10 years. It's a recent reducibility, and I would like to compare it a little bit with the traditional reducibilities in classical recursion theory, and in particular Turing reducibility. There is some immediate difference, which is there is no reduction involved. It is a pre-order, but it shouldn't really be called a reducibility because there is no algorithmic relation between x and y. In the case of Turing reducibility, there is a continuous, effectively continuous functional that maps y to x. There is an algorithmic transformation of y which gives x. But here there's nothing like that, nothing apparent anyway. So a lot of times this class of reducibilities are called weak reducibilities. And they induce degree structure of the k degrees. So let's see some differences and similarities with, for example, Turing, but it applies to the other reducibilities, the classical reducibility is the same. It has the same complexity as Turing reducibility. Turing reducibility can be defined using three quantifiers. It's a sigma 3 reducibility. There exists, for all, there exists. So basically, you say that there exists a program such that for all arguments, the computation gives a certain thing. The last part is one quantifier definable. So all of this, the K reducibility and the others we're going to see in the following are of the same complexity, and that's a similarity. Also, it allows you to mimic some arguments, not all, in fact, quite few arguments from the classical recursion theory, and produce results in those reducibilities, just by the fact they're sigma 3 and they have some other common features. But the degrees are no longer necessarily countable. We have uncountable equivalence classes in the case of K reducibility. The lack of an underlying reduction is a big problem for simulating arguments from the classical theory, recursion theory. And in fact, one consequence of this is that we have uncountable lower cones. Some of the lower cones in this structure, so some degrees have uncountably many predecessors. Okay. So you can see the breakdown between computability and reducibility and definability here, because if a degree has uncountably many predecessors, then, well, it's not possible for each predecessor to be definable in some countable language by that top degree. Okay, that there are only countably many definitions in a countable language. So that causes a lot of differences, and in particular a lot of structural differences, which we're going to see later on. Another point is that the k degrees lack a join operator, and this is true for many other weak reducibilities. They even lack upper bounds. You may have 2 degrees such that no degree is above both of them. Okay, so if 2 degrees are random relative to each other, there is nothing above both of them. Let's see another recent reducibility of the last 5 years or 6, 7 years. This time we want to measure not randomness, but the ability of the reals as oracles to compress programs. So if you use a machine without an oracle to compress programs, you achieve some compression in general. If you use a powerful oracle, you get a much better compression for all programs. If you use the halting problem, for example, you get a dramatically improved compression of programs. So the complexity of programs reduces dramatically if you use an oracle. So in this way, we say that where some strings may be incompressible with respect to x, but compressible with respect to y. For example, they may be random relative to x, but non-random relative to y. So if y can compress at least as well as x, we say this if it compresses every string more than x modulo fixed number of bits. Okay, so in symbols you get this inequality. So you have for every program sigma, the complexity with respect to y is less than complexity relative to x. Okay, and we denote this reducibility by Lk. So if y can compute x, then it can naturally simulate any computation that is performed by x, right? Because it computes x, it can see what it does and simulate it, which means that if y computes x, then y is Lk above x. So Turing reducibility implies this, but not vice versa. The degrees under this reducibility, the continuum is reordered in it looks from far away, it looks like the Turing degrees, but it's not the same. Let's see. 0 prime also plays a role, because, for example, it's above Turing above all computably enumerable sets. Therefore, it's Lk above all computably enumerable sets. There is a list element. There are upper bounds, because you can use the Turing join, but least upper bounds is an open problem. It has the same complexity, sigma 3, as the Turing degrees. The degrees are countable. That's non-trivial. It needs a proof. Some lower cones are countable. Some of them are uncountable. In fact, the degrees below 0 prime form an uncountable class. But there are a lot of structural differences. For example, there are no minimal pairs of computably enumerable degrees. There are no minimal pairs even below 0 prime. All of these are structural differences with Turing. So there are global differences like uncountability of lower corners, but even locally in structures like countable structures, like the degrees of computably enumerable sets. And another difference is that there are very large chains. For example, there is a perfect set forming a chain under LK. This is unheard of in the Turing degrees. It's wrong. There is a very basic theorem by Gerald Sachs which says every perfect set contains an anti-chain of size the continuum of Turing degrees. Okay. So one of the main results in this area in 2003, around 2003, by Andre Nies was the following: that zero compressing power is equivalent to trivial initial segment complexity. So an infinite binary string is k-trivial, as I defined it before, has trivial initial segment complexity, if and only if it's useless as an oracle for compressing programs. So it's as good as a computable oracle, as a machine without an oracle. Okay. Now these are two different notions. One has to do with oracle computation, and the other has to do with the presentation of the information in the bits of the sequence. It doesn't mention oracle computability at all. But surprisingly, they are the same. So two triviality notions are equivalent. In terms of degrees, the equivalence classes, the bottom degrees in these two structures are equal. Okay, that's a non-trivial result. So let me repeat myself. A string cannot compress strings more than a computable oracle, if and only if its initial segments can be described as easily as a computable string. Okay. So this result is, in fact, quite optimal. It says even the fact that something with quite high information, like the halting problem, even this fact that the halting problem cannot be coded into a sequence with trivial complexity needs a serious proof. It's not easy at all. So you're looking at the wrong slide. I'm still on this one. So in a way, this result is optimal in the sense that there are encodings of the halting problem of extremely low complexity, very close to trivial, but not trivial. So what does it mean, very low to trivial? Well, you can measure it crudely by very slow growing functions. The complexity grows very slowly. But even more dramatically, there are results which say, given any say computably enumerable sequence, binary sequence, which has complexity, whose complexity is non-trivial. It could be as low as you want, but not trivial. Then you can find an encoding of the halting problem which is below that, even lower, strictly lower. Okay, but it won't be trivial. So this is in a way a very tight result. So another connection between these two notions is that for random sequences, one is the inverse of the other. In other words, one stream is more random than another, if and only if it has less compressing power. In particular, the more random a stream is, the less oracle power it has, which is, it fits with our intuition about randomness, because the more random a sequence is, the harder it is to code information into it. Information introduces structure in a string. The LK reducibility is a particular case of reducibility obtained by partial relativization. It's an operation that Well, it might have been around implicitly in the past, but it was made explicit recently. So the idea is that you take a lowness notion. In this case, X is low for K if it has zero compressing power. We've seen this notion before. And you relativize it. But if you relativize it directly, so a faithful relativization is when you introduce a parameter in every place of the definition. And this means that you can carry through the theorems relativize. Right? But this is not always the most natural way to do things. For example, if you do this for this notion, you get something which is equivalent to this, which is not what we wanted. In particular, it's not transitive. It doesn't model a reduction for complexity. So it's not what we want. If you try to define this naturally, you will come up with this. So the complexity in the sense of compressing power, you will come up with that, which means that you relativize some part of the definition, but some other you don't introduce the parameter. That's why it's called partial relativization. And in a lot of examples, it makes sense to do things this way. Okay, there are examples like for other known notions like jump traceability, other randomness notions, which have found applications to other areas of computability theory. So let me finish by outlining some of the current research on the topic of reducibilities. That's what I'm talking about in algorithmic randomness. Okay, there is a lot of research not directly related with reducibilities, but as far as this is concerned, a lot of research has to do with similar questions related to different notions of randomness. Well, in the same framework though. Either lower, weaker randomness or stronger, like Borel and beyond even. Some of it has to do with reducibilities on local structures, like effective reals. For example, reals that have an approximation from below, computable approximation. So this was done in the 70s by Solovey, and well, the result is actually more recent, that hardness of approximation in this sense equals the degree of randomness. So the more random you are, the hardest you are to approximate, and in fact the two are equivalent in a very specific way. In particular, this gives rise to a degree structure where the random elements of these effective reals are all in the top degree. Okay, there is a maximum degree, which are basically the halting probabilities of universal prefix-free machines. And there are many open questions related to reducibilities, and a lot of questions in algorithmic randomness can be stated in terms of reducibilities. Okay, for example, well, a basic question is there a maximal k degree? It's open. Very basic questions. I should say that a lot of times, especially with local structures, a recursion theorist confronted with a problem in these weak reducibilities often looks at the situation in Turing degrees or some classical reducibility. Sometimes you can carry through arguments using the similarities, for example, the same complexity and so on. A lot of times you can't. And a lot of times the statements go the other way, are false. Statements that are true for Turing degrees, classical reducibilities, are false here. So in this case, you need new techniques. So a lot of times, because of this, the link between definability and computability or reducibility breaks down. This is basically a place where you need new techniques, and that's a difficulty in the area. On the other hand, you can still use definability as a guide. If you can find local parts of the structure for a weak reducibility, like LK, for example, like some initial segment where the link is preserved, then you are able to prove things there using methods that are not so far from classical regression theory, computability theory. So definability is still a guide, but it's not as useful as it used to be in classical reducibilities. So we also have a lot of questions about local structures, like the computably enumerable sets. Many questions, density, upper bounds, least upper bounds, they are open. And people have looked at them. It's just that a lot of times you have this immediate difficulty that a lot of things you know don't work. You need to think of new techniques. So I'd like to finish with, well, some basic reading. These two books have a lot about reducibilities and the weak reducibilities I talked about. This is more generally about algorithmic randomness. And this is my webpage where you can find some of my work on this topic. Thanks.
Any questions, comments? Barry.
K-reducibility doesn't seem very natural in the sense that it doesn't actually, the reducibility doesn't indicate some kind of help that you're getting.
Yeah.
Questions.
Yes, that's right. I was told to tell everyone who wants to ask a question to stand up and face the audience.
I was just saying that K-reducibility doesn't seem very natural to me because the reducibility doesn't actually indicate some kind of help that you're getting during the reduction.
Okay. But you should think, what are you trying to model? When you want to say that y is more random than x, you don't necessarily want to say that y helps x or even that it's related algorithmically with x in some way. It's just a way to formalize this. There are more uniform ways to do it.
The other reducibility that you've worked on, you do get this.
I've worked on both of them actually, but LK, is closer to a reducibility than K. But again, the algorithmic relation between the two sides is not as strong as in Turing reducibility, for example. But yes, it's more, it's closer.
Any other questions? Now, with this new rule of standing up and facing the audience, no one dares to ask questions anymore. Well, if there are no other questions, let's thank George.